Welcome to EDU World Space.
All right, in this problem, you need to find the moment of inertia of a machine component that is composed of nestled cylinders made out of bronze, neoprene, and aluminum. After you find the moment of inertia, you need to find the radius of gyration k, which is given from the square root of the moment of inertia divided by the total mass m. All right, since we need to find the total mass m of this device, let's start by finding the mass of each of these pieces and adding them up. All right, so the mass given by these cylinders, the mass of these cylinders will be given by rho, the density of the cylinders, times pi times L, the length of the cylinders, times b squared minus a squared, where a is the inner radius of these cylinders and b is the outer radius of the cylinder. Okay, so if we take this formula and apply it to all of our cylinders, we can get the mass. First, for bronze, we have 0.310 pounds per inches cubed. And since everything is given to us in pounds and inches for this problem, we're just going to keep everything in pounds and inches and report our answer in pounds and inches. So 0.310 pounds per inches cubed times pi times 13/16 of an inch times 3/8 inches squared minus 1/4 inch squared is approximately 0.0618 pounds. All right. And of course, some of you might object to using pounds as a unit for mass, but it doesn't matter in this particular problem. We can pretend that mass and weight are the same thing in this particular problem. All right, so the mass of aluminum given by the density of aluminum times pi times 11/16 of an inch. That's the length of the aluminum cylinder. And in this case, the outer radius is 1/2 inch. All right, and the inner radius is 3/8 of an inch, so that's squared. And the mass of the aluminum piece is approximately 0.0236 pounds. All right, and lastly, the neoprene piece, it's going to be given by the density of the neoprene times pi times 11/16 of an inch. And in this case, the outer radius is 9/8 of an inch squared minus 1/2 of an inch squared. And we get, for the mass of the neoprene piece, approximately 0.0992 pounds. All right. So each of these ones, for each of these figures, we can keep three significant figures. So if we add them up, then on the next, then for our sum, we can keep every significant figure to the most exact known digit. So we're going to keep 4 significant figures in our sum. And when we add them up, it's going to be 0.1846 pounds. All right, we're going to use that later. But right now, something that's really useful is before we calculate the moment of inertia for each of these pieces, let's derive the moment of inertia for a generic cylinder, because we'll actually get a really useful formula that'll make the next step really, really easy. So for any cylinder where the cylinder has a density rho and the cylinder has an inner radius a and an outer radius b and a length L, then the moment of inertia of the cylinder around the central radius is given by the integral of r squared times dm, and this becomes a 3D volume integral if we know the density. So from 0 to L in the z direction, from 0 to 2 pi in theta, and from a to b in r, then this is the integral of r squared, and then dm, the integral of dm becomes rho times r dr d theta dz. All right, so that is our volume integral to find the moment of inertia for this sphere. I'm sorry, this cylinder, excuse me. All right, so keep going. A lot of stuff comes out of the integral. The rho comes out, 2 pi can come out for the theta integral, the L can come out for the z integral, and it becomes an integral from a to b in r cubed dr. And then when we solve this or plug in b and a into our integration, we get rho times pi times L divided by 2 times b to the fourth minus a to the fourth. Now, We can replace rho at this point and get something that's really useful. If we remember that rho is given by the total mass divided by the volume of the cylinder, and the volume of the cylinder is pi times L times b squared minus a squared. We can take this and plug this into the our previous result and get a really, really simple formula for I. So this becomes pi times L over 2 times rho, which is m over pi L b squared minus a squared times b to the fourth minus a to the fourth. All right, so the pi and the L cancels, and b to the fourth minus a to the fourth divided by b squared minus a squared gives us b squared plus a squared. That's a result we should remember from algebra 2. So this becomes m over 2 times, let me scroll down just a little bit. Our moment of inertia I becomes m over 2 times b squared plus a squared. All right. Now, this is true for any uniformly dense cylinder with an inner radius b and a. It doesn't matter what the length of the cylinder is. So we can take this formula and apply this to our bronze, our neoprene, and our aluminum piece individually to get each moment of inertia. And then the moment of inertia of the whole thing will be the sum of all three moments of inertia. So first, the moment of inertia of the bronze piece, given by the mass of the bronze piece divided by 2 times the inner radius squared, 3/8 of an inch squared, plus the, oh, I'm sorry, this one's the outer radius. 3/8 of an inch is the outer radius for the bronze piece. And 1/4 of an inch is the inner radius. There it is. All right, so the moment of inertia of the bronze piece is given by 0.00628 pounds inches squared. All right, since everything is measured in inches and pounds, the moments of inertia are given by the units pounds inches squared. Okay, then for the aluminum piece, same steps. The mass of the aluminum piece, which we calculated, divided by 2. The outer radius of the aluminum piece, 1/2 inch squared, plus the inner radius of the aluminum piece, 3/8 inch squared. And this gives us 0.00461 pounds inches squared. Okay. And then lastly, for our neoprene piece, the mass of the neoprene divided by 2, the outer radius, 9/8 of an inch squared, plus the inner radius, 1/2 of an inch squared. And this gives us 0.0725 pounds inches squared. And again, because the each of these figures is known to three significant, each of these data figures is known to three significant figures, so when we add them all up, we can actually keep the last most significant figure, so we'll keep 4 significant figures in our sum, and what we get is the total moment of inertia is 0.08339 pounds inches squared. Perfect. All right, so that is one part of the solution. That is the total moment of inertia of our component. Now what we need to do is find the radius of gyration. I wrote this down earlier, but let's write this down again. The radius of gyration k is given by the square root of the moment of inertia I divided by the total mass m, and in our case, the moment of inertia 0.08339 pounds inches squared. And our total mass is 0.1846 pounds. All right, that's something that we calculated earlier. That's up here. Okay, divide and then take the square root. And what we get is 0.672 inches. So a quick, or 6721 inches, because we can keep four significant figures in our answer. So a quick way to check to see if this is a good answer to see is to make sure that this is no bigger than any of these values here. And sure enough, 0.67 inches is approximately 2/3 of an inch, which puts it right along with all of the values of our radius we were using. If we got an answer here that was much, much smaller or much, much bigger than any of these radiuses, then we would know it was wrong. But this answer, 0.67 inches, is very close to all of these radiuses here, so we know it is on the right order of magnitude. So we're going to keep it. We're going to say that's the right answer. All right, and there we go. Very good job, everybody.